Hello, everyone. Let's finish Unit 1. We're going to finish our discussion today about chiral molecules. So head over to Key Concepts, Unit 1, Part 6 that you found on Canvas. This is page 1 that we already covered in a previous video. So scroll down until you see this section here. Molecules with multiple chirality centers. Okay, so far in previous videos, we've seen molecules that just contain one chirality center. Well, there might be an example or two of two chirality centers. So in general, what do you do if the molecule you are studying has more than one chirality center? Well, just be straightforward and systematic. There's the marker. Get the pen going. There we go. So if you're having to name the molecule with multiple chirality centers, each chirality center is going to need an R or S label. So go review the video on assigning configuration. I'll review that here too. Let's see. You can also, if you have to draw all the possible stereoisomers, here's a good way to see if you found them all. They're going to have a maximum of 2 to the n stereoisomers, where n is the number of chirality centers, right? So if a molecule has 3 chirality centers, put that up here, 3 chirality centers, or handwriting, sorry. Then it has 2 to the 3rd power, or 8 maximum stereoisomers. Oops, got something else going on here. There you go. Now it's maximum because there are cases where you have an internal plane of symmetry. So yeah, it can get a little more confusing. Sorry, you can blame me if you want, I can take the heat, but really nature, she's the one who did all this. Here, let's take a look at an example we saw in a previous video. 1,2 cyclohexane. No, this is cyclopropane. Sorry. You could do that one too, but I got these down here. Little triangles are cyclopropane. 1,2 dichlorocyclopropane. Okay, so in a stepwise approach, maybe you could have said, here's the name, draw the structure, cyclopropane ring with a chlorine on carbon 1 and chlorine on carbon 2. Oh wait, are there chirality centers? Yes, this carbon here is attached to a chlorine. The top of the ring, this carbon's connected by this bond to the top of the ring. This carbon's also connected to the other ring carbon, but this ring carbon's different from the top one because this one has a chlorine attached. This group is different from that group. And then there's the unwritten hydrogen. And there's our test for chirality centers. If there's an atom, most of the time it'll be carbon in this class. Actually, it'll always be carbon in this class. Is that carbon attached to 4 different things, groups? Yes, here it is. A chlorine, carbon with a chlorine, just a regular carbon, and a hydrogen. So yes, this carbon is a chirality center. You can do the same check on the other carbon. Yep, that's a chirality center. We have 2 chirality centers. So there must be a maximum of 2 to the 2nd power of stereoisomers. The next approach is just draw all the possibilities. Your chirality centers are going to have dash and wedge bonds. So look at all the combinations. Here, the chlorines both have wedge, or they both have dash. Or they have one wedge, then dash, or you reverse the order, dash, then wedge. So there are all the 4 possible stereoisomers. However, there's 2 tests for chirality, right? One test is, can you find an atom with 4 different groups? Yes, we did. In fact, we found 2. The other test is if you can find an internal plane of symmetry, then the molecule is not chiral. So if we cut our hand, try and not physically cut it, ouch, but you know, it's kind of mentally try and cut our hand in half. There's no way that one side is equal to the other side, exactly, right? However, this first molecule here, if we cut it right down the middle, it's pretty close to the middle. We have the two sides completely equivalent. They're identical, they're symmetrical. And that fails the chirality test. This is not chiral. The proper term is achiral. It's an achiral molecule. And it is true, it has two chirality centers. But just having just having chirality centers is not enough to make the molecule chiral. Oh yeah, so what does chiral mean? We can go back and review the video, but one test, another test, I guess, is if you can draw the mirror image of it and you try and superimpose the two, they should not superimpose. They're non-superimposable mirror images, very much like my left and right hand. So if I hold my hands to the screen this way, let's get out of the screen sharing so you can see. Quick review, right? So if I hold up my hands this way, hey, it looks like they're the same. Thumbs on this side, pinkies over there. Everybody looks good, but wait, this is the hairy side, this is the palm side. You have to do it the same way, and now things don't superimpose. And if you hold up one hand, oh yeah, I did this before, I got the mirror behind me, there it is. This hand looks like, there we go. So in the mirror reflection right there, that's a hairy side towards you. This is the, I can't turn around really. There you go, this is palm side. If I hold palm side, there you go. This thumb on that side, this thumb on that side if you look at the reflection. So this hand is the mirror reflection of this hand. They're mirror reflections, or mirror images, and I cannot superimpose them with the same orientation. Palms down, they do not superimpose. Hey, these hands are chiral. We talked about how chiral comes from the Greek word for hands. So, hey, these hands are hands. Yeah, chemistry. All righty, where was I at? Oh yeah, so two tests for chirality. To be chiral, it has to pass both. One, you can't cut it in half. If you can, like you did, not chiral. The other test is, can you find an atom with 4 different groups? And really you need to do both tests. Why? Did I save my molecule? I did. Sort of. I'll fix it. So if you look in the little box on the screen here, my little camera, I got the 2 chlorines coming towards you. Hold it like that, chlorines will be green. And if you go to the rest of the screen, that's this model I'm holding in my hand, whoops, represents this molecule here. But if I simply turn it the other way so you look at the other direction, now the chlorines are both going away from you. And that's this molecule. Wait, they're not different. This molecule is the same as this molecule. You're just looking at it from different sides. These two are the same. So really, draw one, both wedges, that's the same as drawing both dashes. It is. So really, I got the same molecule drawn once. This one is different from that one. You have to draw molecules, you have to build them with a model kit, marshmallows and toothpicks maybe. Convince yourself they're different. So really there's a total of 3 stereoisomers, not 4. That's why we got that word maximum number of stereoisomers is 2 to the 2nd power. It's not always true that's going to be exactly 4. Sometimes it is, but in this case it wasn't. Okay, nice review there. I think. Let's try it again. All righty. Oh, new term, right? Chemists, scientists in general. Every time there's a new idea, we need a new word, a new label for it, a new term. Okay, so these are 4 stereoisomers of 1,2-dichlorocyclopropane. However, the 2 wedge and the 2 dash molecule, they're the same. That's a new idea. We're going to call that meso or meso. This one molecule, I've drawn two different ways, both wedges, both dashes. You could just call it the Meso compound or the meso, right on the screen. This molecule's IUPAC accepted name is meso 1,2-dichlorocyclopropane. Yep. New idea, new term. Cool. All right, let's do another example. Because I know this is kind of subtle. It's not. I'm glad if you're getting it. But if for those of you who are just like, give me another example. There you go. Let's look at 2,3-dibromobutane. Okay, so if the question was draw all the stereoisomers of 2,3-dibromobutane, you might have said, okay, I'm gonna draw my butane, 4 carbons, right? Mabel eats peanut butter, butyl, butane. Whenever you draw it, you get to decide how you want to number it and how you want to draw it. So let's number from, I'm going to decide to number from left to right. So here's carbon number 2. I'm going to attach a bromine here. Might as well just do it the regular skeletal drawing. And then this carbon is number 3. That's going to get my second bromine. And now here's a skeletal drawing of just 2,3-dibromobutane. But this represents this one drawing represents all of these molecules drawn on the screen. Yeah. So if the question was, well, draw all the stereoisomers, then this drawing's not enough to represent them exactly. This is, if we draw this one molecule, it means I have a mixture of all these other molecules. So on the exam, I might ask you, give me the stereoisomers individually. Okay. In that case, just start putting wedge and dash bonds on the chirality centers. Oh, where are the chirality centers? On carbon 2, got a methyl, a bromo, and a 2-carbon group with a bromine on it. And then the unwritten hydrogen. Hey, that's 4 different groups. This is a chirality center. And carbon number 3, same deal. It's also a chirality center. Molecule has 2 chirality centers, so there's 2 to the second power, or 4 possible, or maximum. Maximum stereoisomers. And then just get systematic. Just get, go through all the combinations, right? So my marked up drawing here at bromine, carbon 2 and 3, well, maybe they were both on wedges. That's one possibility. Maybe they're both on dashes. Maybe I have the first bromine dash, second bromine wedge, and then I'll reverse that. Let's make the first bromine wedge, second bromine dash. And those are all the combinations of dash and wedge bonds. And hey, I drew my 4 maximum possible stereoisomers. But then what the question was, well, are there any meso compounds? To find that, you need to see where can I divide this molecule in half so the one half is exactly the same as another half. And you suspect it's right along here because you get 2 carbons on one side and 2 carbons on the other. But this bromine's up high and this bromine's down low. That's not the same. It's not, is it the same? It's, do you spin this? And it's hard to tell. I think it'd be done. Some of you probably can mentally rotate this group so the bromine is like over here and the methyl group is on the other side. And then you can check and see if this is the same or not. It's not. This is not a meso compound. Yikes. It's difficult. And you don't get a model kit on an exam because it'd be easier. I don't know about easy, but it'd be easier if you had a model kit and you can build it and just take a look. Take a look. So I did prepare this in advance. Yeah, let's just do this. Let's show, let's get out of the screen share. And there it is. And let's find out where is a symmetry plane? Where is an interplane symmetry? So what do I have here? Let's draw the molecule, show the molecule here, maybe up in the corner of the screen. Don't have a nice white background, but you can see that the carbons, let's focus on those carbons first. 4 in a row, zigzagging like a normal skeletal drawing. And then right here, this one here, this carbon, that's a bromine. The yellow one's going to be bromine. It's towards you. That looks like that's on carbon 3. I'm hoping I got the right point of view that you do on the video. And then it looks like carbon 2 is away. So we got a dash bromine and a wedge bromine. Now what I'm going to do is just rotate this 180 and spin it this way so it's a little easier to see. And now you can see that in, I hope you can see the internal mirror plane. You cut it this way, and guess what? I can just break it. There we go. And you can see that the 2 yellow bromines are towards you. I'm holding on to 2 methyls, and then there's these hydrogens that are away. These are mirror images of each other. These are identical groups. Right, so this side looks like this side. This is 2 halves of a molecule, and each half matches. So this is the meso compound, where I said what, 1 wedge, 1 dash? Or was it 1 dash, 1 wedge? Let's check. Okay, so if you zigzag it this way, then I have, let's see, so let's just try and get our orientation straight. So I'm zigzagging the butane chain, and I start up high. So there's a carbon up high, then down low, up high and down low. And it looks like second carbon is away. Sorry, that's a bromine. Second bromine is away. I didn't rotate the molecule. I just spun it and flipped it. And I got the carbon up high. Second carbon has the bromine towards you now. You rotate it this way. Rotate it this way. Now the bromine on carbon 2 is away. Oh my gosh, it's the same molecule drawn twice. My screen share. We got the answer. It's 1 wedge, 1 dash. Whether the dash comes first or second, doesn't matter. It's the same molecule. So that is this one right here. Here's bromine on a dash bond. And here's a bromine on a wedge. This is actually a meso compound. And so it's also true that the bromine on a wedge first and then bromine dash is also the meso compound. These 2 are the same. And we have 3 stereoisomers again. Breath. Okay. Now it's kind of cool that we can figure it out using a model kit, but we can't use this thing on exam. And you know what? It's actually kind of cumbersome to do that anyway. So you have to figure out, okay, there's a better way. This guy with last name Fischer, was it Emil? I'll have to go back and look. Anyways, he discovered a better way, a better tool for finding meso compounds and drawing stereoisomers. Let's see, let's just finish this page right here. Yeah, so we already came to this conclusion at the bottom of our key concepts page. It looks like there's 4 stereoisomers. I drew 4 drawings of all combinations of dash and wedge. Looks like there's 4 of them. But if you build a model kit, which we did, you'll find that 2 of these, last 2, are exactly the same. So I drew the same molecule twice here at the end. These 2 are the same. So there's really only 3 stereoisomers. Check the stereochemistry in a minute. Oh wait, where'd it go? Down here, Fischer drawings. I hit them down below the page. It's not hidden, it's just out of the way. Okay. Here's another way of drawing molecules, right? You've seen condensed structures, full structural drawings, skeletal drawings, Newman projections, chair conformations. All these ways. Aren't we done with different ways of drawing molecules? Nope. One more way, Fischer drawings or Fischer structures. Okay, so these are vertical drawings. So the carbon chain is aligned up and down. And again, when you're drawing Fischer, you decide how you want to draw them. You want to draw all the bonds This person said, nope, I'm doing a condensed CH3 group. I'm not drawing the bonds through the hydrogens. In the middle, they said, I'm going to switch back to skeletal drawings. The intersection of a line of lines indicates a carbon. So there's a second carbon here, third carbon here, and the fourth one down there. The standard way of numbering a chain is to put carbon 1 at the top. And you go down the chain, the highest numbered carbons at the bottom. Everything's vertical, right? So this is not the right shape of the molecule. Bond angles are not 90 degrees. That's an sp3 hybridized carbon. It's supposed to be 109.5. But this is a Fischer drawing, and it's just understood that the carbon chain has been just artificially straightened out. Not exactly. Okay, let's screen share. Oh, stop the screen sharing and look back at our model. Okay, so this is what the Fischer drawing is trying to attempt to draw. Or the shape of the molecule we're trying to draw. So we start with the zigzag chain, which is more of a normal shape. Actually, this is the more stable shape. You know, everybody, if you look down, ooh, that's not good. There we go. Look down these carbon chains. Try it again. There we go. Now we can start staggering stuff. Kind of viewing this from a Newman projection point of view. This is the most stable conformation, most stable shape. Everything is zigzagged. Staggering here. The two bromines are opposite. They're anti. Cool. All right, where were we going? Fischer drawing. So take the most stable shape and make it unstable. Bend the chain so it's more in a line. So I got the carbons up and down, right? And I can pull on them a little bit to try and straighten out, but it isn't. I can't straighten it out. It's curved. It's like the letter C, if you look at the carbons. But if you draw it this way, and those of you who've had an art class, if you just look at this, what is that called? Projection. If you just look at the 2D projection, and for those of you who haven't had an art class, I mean, just on a piece of paper, try not to draw it three-dimensional. How would you draw the chain of carbons? Well, you put one up high, the next one below it, third one below that one, and the fourth one back here, just below that. You draw all the carbons in a line. And that's what the Fischer drawing is supposed to do. And as I'm holding this, let's look at carbon 2 here. The bromine is coming out of the screen towards you. So is a hydrogen. And if I draw the molecule like this, now the hydrogen, carbon, bromine atoms look like they're in a straight line, two-dimensional. Right? They're not. It's tetrahedral carbon. But if you look at it this way, it looks like it's HCBr on the line. That's that flat line in the Fischer projection. And it turns out, anytime you see a flat line, horizontal line, that's understood to be wedge bonds. This hydrogen's wedge bond coming out of the screen towards you, so is that one. Vertical lines are opposite. So if you look at the top carbon, the second carbon, the third carbon, they look like an L line, the vertical up and down line, but really they're fading away from you. They're on dash. They're on dash bonds. So from this carbon back to this one, this carbon's going away. And if you start on this carbon, go to this one, this carbon's going away. So vertical lines are understood to be dashed, fading away bonds. Horizontal bonds are wedge bonds coming towards you. And if you look at carbon 3, it's the same orientation, right? So just twist it up until these three atoms are in a line and the top bonds are in a line too. So this bond is up, that bond is up, but it's going away. The up-down bonds, vertical bonds, are dashed. The left-right bonds are wedge coming towards you. That's a Fischer drawing. Okay, so down here is still a Fischer drawing, but there's a lot of detail, takes more time to draw, so most people do not draw it this way. But when you are drawing any structures in my class, you get to decide how you want to draw. If you say, I don't even like skeletal drawings, I'm going to put C's here, that's perfectly fine with me. You get to decide how you want to draw. For me, though, I'm probably just going to draw like this because it's so much faster. So the carbon is at the top, and if I just leave it with no other atoms here, it's understood that the end of a skeletal drawing is a carbon, and I only see one line coming from the end of this line. The carbon bonds 4 times, the other 3 bonds are to hydrogen. Left and right, hey, this is the end of the line. That's supposed to be a methyl. Ooh, no, it's not. It's supposed to be a hydrogen. So I am required to put in the H. Otherwise, you have to erase this horizontal line here. Because you can leave it without, like over here, if I leave the line plain, it means methyl, but no, there's a bromine over here. Moving down to this 3rd carbon, you can decide if you want to put the letter C or not. I'm not going to. It's faster drawing it pure skeletal. But if you draw with vertical and horizontal lines, we have to understand that to mean Fischer. And on this horizontal line, that's really a wedge bond to where the bromine is. Sorry, I forgot to get my phone. Wish I had money. That sounded cool. On the right side, this line ends with a hydrogen. Down below, there's a methyl group, and that line is good. I'm done. That's my Fischer drawing. So, I got that written here, don't I? No, maybe I didn't. Let's put it in here. Horizontal lines equal wedge. That's what the bromine and the hydrogen are on. They're on wedge bonds. And that means it's towards us. And then the vertical bonds. Vertical lines are dashed. And they are away from us, right? So I know this is a plain bond, but if you rotate it so that you're looking at this carbon, the methyl group, so from carbon number 2, the methyl on top is fading in distance. You can see it over here. This is a dash bond. And technically, the carbon number 3 is also on a dash bond. So maybe this should have been dashed as well. That's a Fischer drawing. What's really cool is, okay, so all 3 of these, this molecule up here, this one here, represent the same stereoisomer. And over here, you can see that if I cut the molecule this way, the top half is a reflection of the bottom half. They're identical. Here is the Meso compound. Yay! So if you have a good Fischer drawing, and you can cut it internally some way so the one half's the same as the other half, wait, internal mirror planes mean it's not chiral anymore, and it has chirality centers. So if a molecule has chirality centers, but it itself is not chiral, that makes it a Meso compound and makes it a chiral. Oh, and what if you put this molecule 2R3S23-dibromobutane into a polarimeter and try and see if it'll rotate plane polarized light? What's the angle of rotation going to be? Well, only chiral molecules can rotate light. The angle of rotation, we would use this symbol, maybe it's at 25 degrees, the sodium D line, we can predict it to be 0. This is not a chiral molecule. It doesn't rotate light. It doesn't interact with light. It's not optically active. Okay, that's a great term. The MCAT might choose, right? That's a packed phrase there. Not optically active. What does that mean? A lot of things. It means it can't rotate plane polarized light. It means it's not chiral. If you look at the structure and you see that there's chirality centers, but it's not optically active, then it must be a Meso compound. Cool. Okay. Couple things. I'm going to do another example with the Fischer drawings, starting from scratch. But I also want to show how you can use a Fischer drawing to actually get the R and S configuration. So here's a nice Fischer drawing of the Meso compound, turns out, but the Meso compound still has chirality centers. So if you choose to, right? So if you had to name this molecule, you could, one way to name it is 2s3r 2,3-dibromobutane. But because it's meso, you can also take the shortcut. The name of this, IUPAC name for this is meso 2,3-dibromobutane. That's what I would do. But if I ask the question, okay, what's the stereochemistry of carbon number 2? Assign the configuration to carbon number 2. Turns out carbon number 2, right? So in Fischer, carbon 1 is on top, so here's 2. Turns out that's going to be S. Let's back up one step. In a previous video, we did discuss how to assign configuration. I think I can do this. Okay, maybe I can make it better. So in the previous video, we assigned RNS. I grabbed this other stereoisomer and I thought, let's check carbon number 2. Here's carbon 1 here. Let's see if we can verify that carbon 2 has the R configuration. It's getting kind of busy here. Oh man, I'm busy. I got a whole bunch of stuff on the screen. That didn't toggle. Let's just grab this whole thing. Go to another screen. There's a little more room. Here. There we go. Yay. Sorry, I'm recording all this, trying to clean up the screen and stuff. Someday I'll get a video editor and more time. I'll make this video even better. But this will have to be good enough for now. Let's change colors too. I like orange. All righty. So, how do you assign configuration? Step 1, find the chirality center. Well, we already said we're trying to find the chirality, the configuration of carbon 2. So here's our chirality center. It's got an H, a bromine, a methyl, and then this funky piece of the molecule, this group, and all 4 groups are different. So yay, we found the chirality center. That was step 1. Step 2, rank those 4 groups. Okay, hydrogen is atomic number 1, right? And the higher the atomic number, the higher the ranking. Hydrogen, sorry, you lose. You're the first element. Yeah, but 1 is the lowest number, so you take 4th place. Bromine, is that element 35? Anyways, quick little periodic table. The elements, you don't have to memorize them, but if you work with the table, periodic table long enough, it just sinks in naturally. Okay, so there's a section of the periodic table. And right, atomic numbers increase going to the right, increase going down. Yikes, bromine's way down here. I think it's element 35. And that beats out carbon, which is element number 6. And totally beat out hydrogen. And then this atom over here is also carbon, element 6. So yeah, bromine, you took 1st place. And this methyl group is tied with this carbon attached to a bromine. So to break the tie, you go to the atoms that are tied currently, this C and this C, and ask, okay, what are the 4 bonds, 4 atoms that this carbon is attached to, and ignore the one you already did. So moving away from the chirality center, what are the next 3 bonds? Well, the next 3 bonds are attached to H's. For this carbon moving away from the chirality center, what are the next 3 bonds? Attached to a C, a Br, and an H. And now I pretend they're playing poker. It's high card wins. This poor carbon's holding the 3 lowest cards, 3 H's. This carbon says, should I play the carbon or the bromine? No, I'm going for I'm playing the bromine, element 35. That beats out element number 1. So this carbon just broke the tie and took 2nd place. Methyl, sorry, you got the next place, 3rd. That's step 2, we rank the 4 groups. Step 3, look at the molecule such that the 4th group is away from you. Ah, yay! It's already on a dash bond. It is drawn correctly, so we can trust our configuration. Whatever we decide it is, That's what it should be. Okay, fourth group is away from us on the dash bond. That was step 3. Step 4, look at the orientation of going from first, the second, the third. First, the second, the third. First, the second, the third. And think of that as a steering wheel that you're rotating. And I'm making a right-hand turn. Oh, this is the R configuration. Yeah, so it's true. We just checked it. Let's go back and do the same thing with the Fischer projection, because you can. Oh yeah, so we just checked the normal skeletal drawing with dash and wedge bonds. Now let's do a Fischer. Okay, and let's check carbon 2. So starting at the top of the Fischer is where carbon 1 is supposed to be. Carbon 2 is this one right here. Okay. That was step 1 of assigning configuration. Where is the Chirality center? All right, we're doing this one, carbon 2. Step 2, rank the 4 groups. Okay, so going to the left, there's a hydrogen. Sorry, hydrogen, you're grabbing 4th place as the lowest atomic number. Going to right is bromine. That's going to take 1st place because it beats out the carbon, element 6, and this other carbon, element 6. Tiebreaker is what are the next 3 atoms attached to each of those tied carbons? Well, this carbon's got 3 H's. I know it's 3 of a kind, but that's not the game we're playing. We're playing high card. Sorry, methyl group. You're gonna lose. This carbon's saying, I got a 6 and I got a 35. Bromine's only 35. That totally beats out hydrogen with 1. So this carbon takes 2nd place. The methyl takes 3rd. That's step 2. We rank the 4 groups attached to carbon 2. Step 3, look at the molecule so that the lowest rank group is away from you. So what kind of bond is horizontal in a Fischer projection? It's a wedge. Come on, screen. I need it to be dashed. Sorry, you don't get the dash. Dennis, what's going on? What happens when the molecule is not drawn correctly and the 4th rank group's on a wedge instead of a dash? It means we change our answer. This configuration is either R or S, 50-50 shot. If it was pointing away, we could get it right. But because it's pointing towards us, we're going to get it wrong. So we just change our answer. So this bond is wedge. Step 3 says, no, the 4th group should have been away. And I'm saying, I know, but this is what I got. So change your answer. Well, what's the answer it looks like it is? Well, 1st group goes to 2nd, goes to 3rd. 1st group goes to 2nd, goes to 3rd. Looks like I'm making a right-hand turn. Yeah, but the 4th group is on a wedge bond, so it's not right hand, it's a left hand, which is sinister, S. That is the correct configuration. So it looks like it's R, but that darn 4th group should have been on a dash bond. It isn't, it's on a wedge. Fischer drawings are horizontal, bonds are a wedge. So you have to change your answer. It is not R. It totally looks like it should be. Yeah, but the bond is drawn, the molecule is drawn incorrectly for the correct configuration. So it's not R. Switch it, it's S. Nice. Cool. All right. Let's take a look at this page. I forget something. Yeah, some terms. You got meso. We know that one. If you find your internal mirror plane, there it is. Top half's the mirror image of the bottom half. Here's the plane of symmetry. That's not a chiral molecule anymore. Same is true for this one. Those are meso. And yeah, it is true. The internal mirror planes go down here. Yeah. Meso compounds are really easy. I hope easy for you to identify when they're drawn in the Fischer drawing, not in the zigzag dash wedge fold drawing. Enantiomers. Okay, so if we think of a different mirror plane, like if we put a mirror coming out of the screen right here, and we said, hey, let's look at this molecule in the mirror. What would the image in the mirror be? This thing over here. And if you look at this molecule, its mirror image is the molecule on the left. These two are mirror images of each other, and you cannot superimpose them. That's the definition of enantiomers. They do not have an internal mirror plane. Can't cut this molecule in half, right? If you cut it here, the bromine reflects onto the hydrogen. That's not the same. So this does not, you can't cut it here and have two symmetrical pieces. Nope. And I can't cut it any other direction, up, down, diagonally. Nope, there's no other way to cut it. So one half is a mirror reflection of the other. These are different molecules. They are chiral. They have two chiral centers each. Mirror images, can't superimpose them. The name of that is a pair of enantiomers. Okay, so just to refresh, we definitely need to know what enantiomers are. A pair of non-superimposable mirror images. Meso compounds, that is one of the stereoisomers that actually has an internal mirror plane. Let's do diastereomers now. Scientists, every new idea needs a new term. Ooh, so now we say, hey, these two molecules are both meso. Well, no, it's the same compound drawn twice. So what's the relationship between this molecule here and this molecule there? It's the same thing. Same, that's a relationship. They're the same. What's the relationship between these two? Enantiomers. One is the mirror image of the other, and they are different molecules. They're mirror images, but they don't superimpose. New idea. What's the relationship between these two compounds? One of the enantiomers, I picked the 2s, 3s, compared to the meso. Well, first of all, they're not mirror images, right? So if I put a mirror here and say, okay, take the meso compound reflected in the mirror, you're going to get this molecule. This one is the mirror image. Oh, by the way, they do superimpose the two mesos. If you build a model, you can just turn this one upside down. So the bromines, if you turn upside down, will be on the other side. They're the same. So this is the mirror image of this molecule, and it's not a match. These two are not mirror images. You also can't superimpose them. They're not the same molecule. Wait, that's all the terms we have so far. They're either the same or they're non-superimposable mirror images. This is a brand new relationship. These are stereoisomers that are not mirror images, and they're not superimposable, and they are different. What do we can call this pairing? Diastereomers. So this and this are a pair of diastereomers. The meso compound and one of the enantiomers form a pair of diastereomers. That's the relationship. New idea, new term. Okay, so one definition is it's a pair of stereoisomers that are not enantiomers. They're not non-superimposable mirror images. The other idea is that very frequently, if you have in the laboratory a pair of enantiomers mixed together, it is very difficult to get those two molecules away from each other, to separate them. So in the laboratory, when we do an experiment, we make a brand new compound. If we create new molecules that contain chirality centers, nature is going to give us, a 50-50 mixture of each one, usually. There are some exceptions to that we're going to explore next unit. This case where you get a mixture of two is really common. So new term, new idea. It's called a racemic mixture, or it's a racemic. So I want you to be familiar with that. Those are terms you'll see in the homework, maybe on an exam. So what's a racemic mixture? A mixture of two enantiomers. All right, let's end on this one, I think. Let me double check, make sure I didn't forget something. Nope, got one more idea after this. Okay, another example of Fischer drawings. And we'll put it in the context of an exam, right? So put some value on it. So this is a standard question that I frequently ask. Hey, draw all the stereoisomers of, and then I'll pick a molecule. So on your exam, it's not going to be 2-bromo-3-chlorobutane, but it'll be another molecule. But if you follow this procedure, you can get 100% correct on it. All right, step 1, draw all stereoisomers of 2-bromo-3-chlorobutane. Afterwards, label all your pairs of enantiomers and all your pairs of diastereomers. Also, indicate or label any meso compounds. And if you leave it blank, I'm not going to give you points. You have to tell me there's no meso compound. I need to know what you know. So indicate it clearly on your exams. All right, so what do? So one idea is start with the basics. Let's change the name, the IUPAC name, to just a regular skeletal drawing. So 2-bromo-3-chlorobutane, butane. Mabel eats peanut butter. Butter is 4. 4 carbons is 4. 4 carbons in a chain. I decided to go skeletal. I'm going to number from the left side. So here's carbon 2. It's going to be a bromine attached to carbon 2. And carbon 3, there's a chlorine. Yay. I get partial credit. I will award partial credit if you correctly draw something. So on my exam, show your work, scan it, and upload it so I can grade it. Okay, this doesn't represent a particular stereoisomer. I need to break it down. So one idea, the bad idea, is to go and draw all combinations of wedge and dash. But we're also going to have to go after meso compounds. And when you have more than one chirality center, it's best to draw a Fischer. And even sometimes if you have one chirality center, maybe it's better to draw a Fischer. Yeah. Why not? 2 or more is the ideal time for drawing Fischer. So this is carbon number 1. So that's going to be at the top of my Fischer, vertical line from carbon 1 to carbon 4. Here's carbon 2, and there's carbon 3. And maybe I jumped the gun here. I guess you can too. You're told to look for stereoisomers, so I guess you can correctly assume there are chirality centers. So where are they? Well, not carbon 1, there's 3 H's, and a chirality center has 4 different groups. It's not carbon 4, there's also 3 H's, 3 hydrogens. Hydrogens are identical to hydrogens, so this one's not chiral. Yeah, carbon 2 is, and carbon 3. So I'm going to take a shortcut on my Fischer. I am not drawing all the bonds to the H's because this is not a chirality center. Carbon 1's not. You can though. You could say, okay, there's carbon 4. Legal, totally acceptable, but kind of confusing because at a glance it looks like, wait, are there really 4? I'm sorry, 1, 2, 3. Are there really 3 chirality centers? No, there's only 2. So most people won't do that. They'll just say, well, this last carbon's not chiral, so why show the dash and wedge bonds? That's helpful for analyzing chirality centers, and carbon 4 is not a chirality center. All right. This is a chirality center, and this is a chirality center. 2 of them gives me 2 to the second power 4. So I already know there are 4 maximum stereoisomers here. So let's just get 4 drawings going. Got 3 of them. Here's the 4th one. Cool. And now we want all combinations of placing the bromine and chlorine left and right. All right, so our chirality centers, I took care of all the carbons of the molecule. I'm left with the H's and the halides on carbons 2 and 3. So we could put both halides on the same side. We could put them on opposite sides together. We put the bromine on the top left, chlorine bottom right, or we can reverse that. Put the bromine on the top right, chlorine on the bottom left. That's it. Those are all the possible arrangements of bromine and chlorine on carbons 2 and 3. Cool. If I walk away, I'm going to lose points because it looks like this molecule has 2 methyl groups. So you must go back and add the H's, or it's legal. You could erase these bonds, and it'll be understood that the missing bond is a bond to hydrogen. I already drew the line, so I must have just cap them with H's. Done. Okay. I'm going to get a lot of points because I have drawn all stereoisomers. Let's go down and answer the meso compound. Do we have any meso compounds? So attempt to split them in half. And you'll see that I got a hydrogen, I got a pair of halides, I got methyls. It looks pretty good, but no. Bromine's not the same as chlorine. This is not a meso compound. Same is true here. Bromine and chlorine don't match. And this is even more of a mismatch. A bromine and a hydrogen and chlorine. If I try and cut it this way, nope. There are no mesos. There really are 4 stereoisomers this time. We hit the maximum. There are 4 different molecules of 2-bromo, 3-chlorobutane. Cool. Okay, let's find the enantiomers. Okay, so think of a mirror plane and ask, okay, if you're reflecting this molecule to that one, is everything lining up? And what I mean, maybe you had an art class where you had to draw mirror images. What you do is you draw a mirror plane, and then you measure this distance from the plane to your first group, and on the other side, make sure that group, the H, is the same distance away. So from here to here is methyl, here to there is methyl. Ooh, that's a match. Here to there is bromine. Yep, that's a match. And just see if your groups are the equal distance away from the mirror plane. And they all are. It's a total match. This molecule is the mirror image of that one. And we already said there's no meso, so these can't be the same compound. They must be enantiomers because they are mirror images of each other. This is one way of doing it. I've had other students say, this is molecule 1, here's molecule 2, here's molecule 3, here's molecule 4, and molecule, sorry, screen 1 and 2 are enantiomers. Cool. Do we have any other pairs of enantiomers? Well, let's check 2 and 3. Hey, bromine's matching up if I have a mirror plane right here. Ooh, wait, chlorine and hydrogen don't. These two are not mirror images. Hey, wait, they're not a meso compound either. What's left? Diastereomers. So compounds 2 and 3 are diastereomers. Now we have to find all the pairs. That's what the question says, all. You can get points for every pair you find. All right, what about 3 and 4? Well, the H's match, the chlorines match, the bromines match, the other hydrogens, the other methyl, yes. These are mirror images of each other. 3 and 4 are also enantiomers. Did it find all combinations? Nope. So now we have to be systematic. Let's start with the compound 1. Let's match it up with the other 3. So matching 1 with 2, what's the relationship between compound 1 and 2? Enantiomers. Already did that. What's the relationship between 1 and 3? Oh, 1 and 3. Well, on compound 1, the chlorine and the bromine are together, but 3, they're on opposite sides. Those are different. Not mirror images, and they're not meso, they must be diastereomers. Okay, 1 and 4. Well, same situation. In compound 4, the bromine and chlorine are on opposite sides, but in compound 1, bromine and chlorine together. So 1 and 4 are also diastereomers. Starting in with 2. 2 and 1. Yeah, that's the same as 1 and 2. 1 and 2 are enantiomers. 2 and 3, Did that one already. 2 and 3 are diastereomers. 2 and 4. Well, 2's got the halide, same side. Compound 4 has opposite. 2 and 4 are a pair of diastereomers. And I found all the combinations of 2. It might be done. Let's check. 3 with 1. Yeah, that's the same as 1 and 3. Diastereomers. 3 and 2. No, that's same as 2 and 3. 3 and 4. Yeah, I did that one. That's enantiomers. 3 and 4. Let's check 4. 4 and 1. Oh, that's, here it is. 1 and 4 are diastereomers. 4 and 2. That's same as 2 and 4. That's way over here. Diastereomers. 4 and 3. Yeah, that's 3 and 4. That's enantiomers. Yay, that's it. We did it. Okay, so give yourself some time on the exam. You're very likely to get this type of problem. Last thing, why? As a student, depends on my spirit, my enthusiasm. Sometimes I was like, oh, this is really cool. Yeah, I want to know more. This is awesome. Other times, like, I'm burnt out. Why are you making me identify diastereomers? That sounds so weird. Isn't it useful at all? Okay, let's try and give it some value, give it some meaning. It is useful from the chemistry point of view. So first of all, we did discuss in previous video that enantiomers are incredibly alike. They're very hard to separate because they're so darn similar. But diastereomers are easier to separate because they're less similar. So that's the main reason. If you do a chemical reaction where you create molecules with multiple chirality centers, every pair of enantiomers that you create would be very difficult to separate. But you can get them away from the diastereomers more easily. There's more hope for it. It turns out chemists have gone a long ways. There are ways of separating the enantiomers, but it involves some specialized equipment and money. So we try and avoid getting racemic mixtures, pairs of enantiomers, because they are difficult to purify. Okay, diastereomers are easier to separate. So I want to give you an example rather than just take my word for it. Let's do an example here. So what's cream of tartar used for? Is there some cookies that you might bake that? I don't use that in any of my recipes, but I do actually have a can. It's not Schilling brand, but you go down the spices aisle. You can buy cream of tartar, which happens to be the potassium salt of RR. Is it tartaric acid? I don't know. This molecule right here. And it's a byproduct of the wine industry. It comes out of grapes, crystallizes out, filters out of the wine, and they sell it. The wine companies can get more money. Turns out nature in grapes only makes this form, this enantiomer. It doesn't make the non-superimposable mirror image. We can do it, chemists can find a way to make it in the lab. Maybe there's some other natural products, not grapes, maybe some other plant or animal, I don't know, might make this compound and it's the mirror image. There's also the Meso compound. Ooh, how's it meso? Well, this drawing, introducing another way. This is called the sawhorse drawing. Okay, that's not on the exam. It's less useful. Here it's not too bad. You can see that the first spoke of 3 groups is matching the second set of 3 atoms. Hey, you cut along this line here, you'll have 2 mirror images. This is the Meso compound. And then scientists have obtained pure quantities of all 3 stereoisomers. This one being the easiest to obtain, just filter it out of grapes. You have to make this one and crystallize it and make sure it's pure. And then this one, again, you have to make that, crystallize and make sure it's pure. And how come this doesn't rotate plane polarized light? Oh, because I just said it's meso. It's not chiral. Only chiral molecules interact with plane polarized light. This one's chiral. It's got a pair of chirality centers. Rotates it in a counterclockwise sense. And hey, the other molecule rotates it by the same amount, 12.4, in a clockwise sense. And these are a lot alike. The natural form of tartaric acid melts at 172, so does the enantiomer. The meso compound doesn't melt till 210 though. So what if someone was messing around in the lab and spilled crystals of all three of these in a big pile and scooped up and put in a container and said, oh, sorry, I mixed all your stereoisomers together, and you're like, okay, I have to separate these. Well, one thing you could do is gently heat up the mixture crystals to 173. What would happen? Well, as long as you didn't crush these crystals and get them in contact with each other, they're fairly spread out, maybe on a big pan, put it in an oven. Well, at 173, these two crystals have melted. So now there's a big puddle on that pan, except tartaric acid has not. So very quickly before this liquid tries to dissolve this solid, scoop out these crystals because they haven't melted yet. So that's a quick procedure. I know it's kind of tedious and quickly separating it. There's a process called, is it called zone melting, zone refinery? There's a mechanical process that uses this characteristic, gently heat something up and then semi-filter it. You can look it up. It's a cool procedure just by using temperature to separate compounds. So this one's going to remain a solid. These other two are going to melt. Separate solids from liquids is fairly common. So you quickly get the diastereomer, the meso compound, away from the pair of enantiomers. That was the purpose of this example. If you have questions, email me, and I'll see you in the next video.